Hello and welcome. Today we're going to be talking about projectile motion. Projectile motion is the motion of an object when it is thrown, launched, or somehow put into the air so that it's moving both vertically and horizontally at the same time. Now, so far we have talked about things moving horizontally back and forth. And we've also talked about things moving vertically, whether they were thrown upward or dropped from a height. Um, we've talked about things moving horizontally, we've talked about things moving vertically, but we haven't yet talked about that happening at the same time. And that's what I want us to focus on today. So before we talk about projectile motion, let's review a couple of topics about horizontal and vertical motion. Let's review the way objects move. Let's say that we have a flat ground and that I have some kind of object, um, a a ball or something that is going to slide along the ground, and we're gonna ignore friction for now. We're gonna disregard friction. So maybe instead of grass, I should have said that we're on some large ice rink. Um, but we're on something where we're going to ignore friction. And let's just say that it is pushed with a velocity of 5 meters per second. That would mean that every second it would move 5 meters. And so could represent that like this. Okay? And every second the object is moving the same distance in this direction. All right. Now, what if instead, though, what if I had an object that was dropped? So let's just take the same object and let's drop it. So if I take it and just release it, it's going to begin to fall. So it would start at rest, and then it would fall first a little bit, but since it's accelerating under the influence of gravity, that means that its velocity will continue to increase. So it will cover more and more distance every second. So at first it only covers a little bit of distance, but then as it speeds up, it covers a little more in the next second, a little more in the next second, a lot more than what we started off. And wow, by the time it's fallen for several seconds, we're falling a lot more each second than we were in the beginning. What I'd like to do now is I'd like to take these two ideas and put them together. And let's say that we have an object. Again, let's just let's put it on the edge of a cliff. And let's say that we have our object here, and that it is kicked off of the cliff at, again, 5 meters per second. Now, we're going to neglect air resistance for the object as it flies sideways, just like we neglected just like we neglected friction when it was sliding along this ice rink over here. So maybe it's thrown perfectly sideways, maybe it's just kicked off of the ledge, who knows? But it is propelled at 5 meters per second. And in the first second, it's going to go 5 meters, but it's also going to drop this much. And so I'm going to have it drop like that. So it will end up at this point. And I'm just going to mark that with a blue dot. So maybe blue's not the best color. That's not showing up well. Let's mark it with maybe a nice orange. Okay. And in the next second, it's going to again travel 5 meters. And this time it's going to fall this much. So it ends up at this point. In the next second, let's say that it falls in the next second, it's going to again move 5 meters. But this time it's going to fall this far. And then in the next second, again 5 meters. But this time, this far. Because it's speeding up in the vertical direction. And so you can see what's happening here. And at this point, if I connect these dots, we can see its path is actually going to travel in kind of a parabola, or sort of half a parabola. And what happens is it's traveling sideways at a constant rate, but it's falling vertically at an accelerating rate, and so it ends up making a parabola. And that is going to be the fact that the vertical acceleration does not at all change the sideways constant velocity is going to be a major theme in projectile motion. So what I want us to say about projectile motion, let's just write a few facts down. First of all, let's write down that the motion occurs in both the x and the y dimension. X and the y dimension. Right? Number two, the x dimension has no forces acting on it. And so it has no acceleration. The acceleration in the x dimension is 0. So the velocity is constant. In the y dimension, we have this little force called gravity. The y dimension has gravity acting in it. So the acceleration is 9.8 meters per second squared downward. So I'm going to put a negative sign. 9.8 meters per second squared downward in the y dimension. And here is the most important thing. The x dimension and the y dimension have absolutely no effect on each other. The x dimension and the y dimension are completely separate from each other. completely separate from each other. And that is major asterisks and stars, big idea here. The x dimension and the y dimension are completely separate from each other. And so any practice questions that you work, or any questions that we work with projectile motion, we have to work the x dimension and the y dimension completely separately from each other. What happens in the x dimension stays in the x dimension. What happens in the y dimension stays in the y dimension. If you want to figure out x questions, you need to use x information. If you want to solve for y quantities, you need to use y information. The fact that the y dimension was accelerating did not change the constant sideways velocity in the x dimension. And the x dimension did not affect the y dimension. But together, they both end up influencing where the object ends up. And so, yes, they both influence the object, but they do not influence each other. Each one has its own effect completely separately. And so we can solve the math for each side completely separately as well. All right. Let's take a moment and let's just I'm going to kind of clear the board here, and we'll work a practice problem. All right. So let's say, as we introduce projectile motion, that let's look at this one. Let's say that we have a rock that is kicked off a cliff with a velocity of 8 meters per second. It takes 4.6 seconds to reach the ground. How high is the cliff, and how far from the base of the cliff does it land? Does the rock land? Okay, so the first thing we want to do is draw a picture. Let's just draw a little cliff, and we'll draw our rock here. And it says that our rock is kicked off the cliff straight off at 8 meters per second. And then that is going to fall in a parabola, like we said earlier, and it's going to fall a certain distance away, and it's going to drop a certain distance downward. This, of course, will be delta d in the y direction, so I'll just call that delta y, and this is delta d in the x direction, so I'll just call that delta x. And so the rock is going to travel, and it asks us, how high is the cliff and how far away does the rock land? So let's start to look at how to answer those questions. Now, you'll recall just a second ago we said that whatever happens in the x dimension stays in the x dimension, and whatever happens in the y dimension stays in the y dimension, and that we're going to work those questions completely separately. So what I'm going to do is I'm actually going to draw a table, and I'm going to separate the x and the y quantities. And I'm going to write an initial velocity, an acceleration, and all kinds of things for each dimension. Now, the velocity in the x dimension is going to be 8 meters per second, and that's because this travels off in the x dimension. You'll notice that I didn't label that as initial or final, and that's because our acceleration in the x dimension is 0 meters per second squared. Remember, we said we're going to ignore air resistance, and so if we ignore air resistance, there is nothing to cause acceleration. So my initial velocity is also my final velocity, because the velocity doesn't change since the acceleration is 0. All right, let's see. Now, I know that I'm asked for how far it travels in the x dimension. And I'm told that the time is 4.6 seconds. Now, I think that that's all the information that we know in the x dimension. Let's see, now in the y dimension, since there is acceleration, we will have VI and VF. And it turns out that we don't know VF right now, but we do know VI. It is launched straight off sideways. That means that all of that velocity is in the x dimension and none is in the y dimension. So it's as if it were just dropped in terms of the y dimension. So the initial velocity for the y dimension is 0 meters per second. Now the acceleration is equal to negative 9.8 meters per second squared. We don't know the displacement, but that's what we're asked for also. We don't know VF. Here's the one thing that we do know that we haven't labeled yet, and that is time. It turns out that time is the one quantity which is the same in both the x and the y. This is the one item which travels between the x and the y dimensions. Otherwise, the x remains in one dimension, the y remains in one dimension, and the two never mix. We can't use this 8 to solve anything over here on the y because it is an x quantity. We can't use this negative 9.8 meters per second squared to solve anything in the x because x doesn't accelerate at negative 9.8, only the y dimension does because of gravity. And so those never cross and never mix except for time. Time is the same in both dimensions. All right, it looks like I have enough information here in the y dimension to go ahead and solve for my height of my cliff. Let's see if I can use my delta D equals VIT plus 1/2 AT squared. And delta Y is going to be what we're looking for. So I'm just going to go ahead and substitute delta Y in place of delta D. VIT is 0, and so that will zero out that term, plus 1/2 times negative 9.8 times 4.6 squared. All right, and so that will give us delta y just by completing that multiplication. So go ahead and take a moment and put that into your calculator, get delta y, and remember that that answer will be in meters. All right, you do that, I'll do that as well, and we'll see if we can fill in the blank. All right, hopefully you've had an opportunity to make that calculation at this point, and I calculated 103.7 meters. And so, you know, 1/2 times negative, and let's put that as a negative sign because because it is happening downward. So that means that the cliff is 103.7 meters tall. Well, how far from the base of the cliff does this land? Let's do exactly the same formula, except this time let's use delta x and work in our x dimension. So delta x equals VIT plus 1/2 AT squared. And this time, our velocity is 8, our time is still 4.6, and our acceleration is 0. So since our acceleration is 0 and always will be in the x dimension, that's going to zero out that term and just leave us with 8 times 4.6, which is around See, double check me, but I think that's about 36.8. I'll double check as well. And sure enough, it is in fact 36.8. So 36.8 meters is how far away that stone lands. Um, all right. I hope that was helpful, and thanks for listening as we start the journey in projectile motion. The most important thing to remember is that you draw a good picture, write your givens down carefully, and separate them into the x quantity and the y quantity. And never use y values to answer x questions. Never use x values to answer y questions. Always keep them completely separate, except for time. All right? All right. Thank you very much, and I hope you have a great day. Bye-bye.